This isn't a hardware universe.
Това, което трябва да кажа днес е, че тази среща се осъществява с финансовата подкрепа на глобалното IEEE Computational Intelligence Society, на което благодарим за финансовата подкрепа. И също на система на Cybernetics Society, за това, че ни представиха финансовата възможност да имаме професор Bezdek като гост днес тук. Какъв е графика за днес? Днес от 11 до 20 октомври ще бъдем заедно с професор Bezdek. Съответно, след края на лекцията има малко почерпка за вас. Съответно, с пълно време, който иска да говори лично с професор Bezdek. За тези от вас, които може да не са разбрали, ние правим този семинар, който ще бъде на 7 септември в Компютационалния университет, който е с доста по-богата програма. По време на втория семинар ти може да посетите втората лекция на професор Bezdek, която ще е свързана с Big Data и съответно се възползвате да чуете интересни лекции от други четирима лектори, които са големи имена в областта на изкуствения интелект. Става въпрос за професор Юри от Италия, който също е голям на IEEE членове. Професор Борис Тилман от Съединените щати и съответно професор Патрик Ванг отново от Съединените щати и професор Георги Домировски от Македония. Така че тези два, които не са се записали към момента, все още имаме възможността да запишете се, заповядайте, започваме в четвъртък по 10 сутринта отново в тази зала. Така, благодаря за вниманието. Ще остава пред ми да кажа професор Йоцов и след което ще вземе професор Bezdek.
Може би това нещо трябва да се сложи, защото много не директно с него, но
уважаеми участници, аз съм председател на чаптера по изчислителна интелигентност за България и искам също да ви кажа две думи относно събитието. Първо, направих проучване, много от хората не знаят, че тези хора, които виждате тук и много повече други, са на Световната конференция по интелигентни системи, която се провежда от утре до 6 в хотел Хемус, започвайки от 9 часа. Заповядайте. Много са. От над 50 страни са авторите на приетите доклади. Значи, поне от 60-70 страни са подадени доклади за тази конференция. Ако не знаете, ще ви дам съвсем малко информация за професионалното ниво на IEEE. В такива области като Data Science и други, включително интелигентни системи и други бързо развиващи се области, 10 от 10, понякога 9 от 10 най-мощни световни списания са на IEEE. Относно интелигентност, разбирам, че за много от вас са студенти или са студенти там, първи курс или докторанти и казват така обикновено, това са много теоретични изследвания, трябва да знаеш много математика и аз ще го потвърда. Има милиарди, трилиони неща, за които трябва да се следи при интелигентната система. И кое от тях важно, кое е маловажно, нали, трябва да се знае. Не случайно руските школи, а те се знаят, че руската математическа школа е много мощна, ако не знаете, се състоят обикновено от поколения талантливи математици, някои от тях велики. Защо така? Ами от родител на дете се предават тънкостите, кое, как, какъв смисъл има и така нататък. Така и тук трябва да се работи умно в тези дисциплини, защото може да се загубиш в огромен брой подробности. Но ще спра до тук с приказки, които може би мислите, че не ви касаят. Само ще кажа, че в тази зала, предполагам, всички имат опит с обектно-ориентираното програмиране. А като пример ще ви кажа, предполагам, че не много хора в тази зала имат голям опит с агентно-ориентирано програмиране. Като пример. Значи, никой не казва, че това е задължително. Те се скъпи, това е ясно. Обаче те изтласкват друго. Значи, дори и да не програмираш, поне трябва да знаеш принципите. Не на многоагентни системи, а точно на агентното програмиране, агентно-ориентирано програмиране. Като многоагентни системи, нали, много се занимават хора с това, като блокчета, всяка програма е агент, не е съвсем така. На нашата конференция по интелигентни системи, която ще бъде от утре, аз съм председател на тази конференция и ви казвам добре дошли. При нас младите учени и известните професори сме заедно. Не правим разделяне, т.е. нямаме студентски сесии. Всички сме заедно и затова и вие можете да се присъедините, ако желаете. Представете си какво е нивото на финансиране на такива неща. Няма да се срещне скоро. Тя е на 2 години конференцията по интелигентни системи. След 2 години ще е в Португалия. Преди 2 години беше във Варшава. Така че пожелавам ви успех и давам думата на световно известния учен Джим Bezdek от Щатите да представи своята лекция. Jim, you understood everything, so you are welcome. I give you the floor.
Awesome, we're gonna start.
Yeah.
Okay. Doesn't make any noise.
I'm not secure.
Doesn't work. Does it work? Yeah, it works. You want to put it on me? Put it on my cap? On my head? Oh, this thing. Okay, I'm not an engineer. Okay, is it good? Can you hear me in the back? No. Because I couldn't hear you. Yeah? Yeah, in my pocket, yeah. Okay? No? Yes? Okay, here we go. Can you read that? Yeah. We can. Really? Yes. Okay. Can you see that? Yeah, it's a big fish. I like it's a fish I caught in Hawaii in 2009. Nice fish. You'll see more fish in this talk. Can you read that?
Yeah.
Yes. Okay. You know, when you use these translators in the computer, sometimes it turns out right, and sometimes the people will look at you, what? That's happened to me several times. So probably try to do this. So, can you read that?
Yeah.
How many people have been to the U.S.? How many people have been to Florida? How many people have been to Pensacola? Well, that's where Pensacola is. It's actually in central time in the United States, west of Chicago, believe it or not. And that's where I live, and that's the kind of fish you catch there. Amberjack, that's a nice fish, so that's probably the only good reason to live in Pensacola. So, this is a photograph of my backyard taken from my house. You can see it's nice, 363 days of the year. Can you all see that?
Yeah.
But you know what happens the other 2 days? This is my front yard after a hurricane in 2004. It's actually a hurricane right now going across Florida, but it's going away from my house, so that's good. Because I lost almost everything in my house then. So just a little geography lesson for you. Here's a fish I caught in New Zealand called a kingfish. Here's the title of my talk. Okay, so it was supposed to be a wireless sensor network, but I added some stuff about streaming data at the end of this talk. There's been an ongoing series of papers that me and most of the other people in Australia, I go to Australia every year for 3 months, have written. That started in 2009, so I just packed everything into this talk from some of these papers. So if the talk doesn't make any sense, right, what I hope you do is get interested in getting the papers, which I can give you, and reading the papers. I just pasted a few different things in different parts of the research. Okay, so we'll talk very briefly about wireless sensor network. Believe me, I don't know. How many people know anything about wireless sensor network? Okay, how many people know a lot about some wireless sensor network? See my hand go down? Because I don't know much about wireless sensor networks. I only know about the algorithms that we use to process the data that come from them. But they're one of the big things, next big things. And I'm going to talk about this model, elliptical summary anomaly detection model. So that's kind of the heart of the talk. I'm going to talk about measuring similarity between pairs of ellipses. That's an interesting topic in itself, kind of a math topic. I'm going to talk a bit about visual assessment, which we use ahead of clustering to try to decide how many clusters might be in a data set. And I'm going to talk about anomaly detection with single linkage clustering and some streaming. I have a couple movies right at the end to run for you. I didn't realize I had as much time for this talk as I apparently do have. I just kind of packed this stuff in at the end. And I have the last chart of this talk tells you that I wear hearing aids, right? Blue and red. This is when I have to listen to Democrats in the United States. It's when I listen to Republicans. I never listen to either one, actually. You see them, and you think, oh, Jim has hearing aids, he can hear me. That's false. Okay, with these hearing aids in, I have about 10% of normal hearing. But I will try to understand you. If you have a question, put your hand up and ask it, please. But I may ask someone else to tell me what you asked me. You understand what I'm saying? You know, it's better to email me. I'm happy to talk to you about anything you want to talk to by email. But I'll try. That's all you can do. Okay, so here we go. This is Shanika. Can you see these people? Upper left corner, Shanika. I can't even say her last name. She's a professor at the University of Melbourne in Australia. Jim Keller is professor at the University of Missouri in the US, of course. Brian is a professor at EE in Melbourne. large part, he's a professor at the Sydney Institute, Western University of Sydney or some damn thing like that. But I met him when he was in Melbourne. And we just had, Sudhar, he's a professor at Deakin University now, but he was the first student that I dealt with down there about wireless sensor network. Tim Havens, he's a professor at Michigan Technological Institute in Michigan, obviously. Chris Leckie, he's a professor of computer science in Australia. Me, I just go where the fish are. Masa Solihi, she's, I guess, going to become a professor at Monash University. We just had a paper accepted on anomaly detection and streaming data last week. And Masood Mustagi, he's a principal young investigator, is what we call him in the United States, at the University of Melbourne. And actually, I don't have a picture of Dheeraj Kumar on here. I should have it. The last thing in the talk, I just stuck it in. Dheeraj, we do with Dheeraj. So these are the main papers on wireless sensor networks. There are some others. I'm going to talk about the 3 that on my computer are yellow, but is this portable? Yeah, I don't know. They don't look so yellow up there. They look kind of puke green, actually. And some other stuff. Okay? Okay. Yeah, what if it's not okay? Wireless sensor networks. The only chart I have about them, and it's everything I know about them. They have sensors, transceivers, memory, processors. Yeah, everybody knows that. This is an old picture, cheap and small. They're probably much smaller than this now, right? This is an American penny. Probably the size of, who knows what they're the size of. They're certainly useful for unattended areas. That's one of the main uses, at least in my past experience, for wireless sensor network. But I gave this talk at Siemens in Munich a few years ago, and one of the guys in the back of the room said, hey, by the way, this room contains wireless sensors. You know, listening to you and watching you. Little video. It's kind of, does that mean? It's kind of scary. Anyway, there are some problems with them, of course. You know, they're battery powered, so you have to worry about power all the time. Probably not so much bandwidth. Memory is limited, and the main thing is the processing capacity is limited. So the models that we've been working on try to overcome these problems. The communication problem, you know, you have the bottlenecks in the networks and so forth. That's what we try to overcome. So here we go. Excuse me. I have a drinking problem. Can you read it?
Yep.
I can see it well on my screen. So anomalies, what are they? There are lots of different kinds of anomalies in wireless sensor networks. You can certainly be attacked. You can have a malicious node. There can be outliers in the data that's collected at a particular node. There can be failures, battery, you can be drift, with low power and so forth. So there's all kinds of things that can happen at a node in any network, really, not just wireless sensor network. And there are lots of different causes in these environmental networks. There's a change. I mean, in these weather networks, there are many in Europe. Actually, we have a lot of our data. There's a huge company in Europe called SensorScope that builds, at least it used to, build many of the big wireless sensor networks that we collect data from on the internet. So you can have things like weather sensor networks, as clouds obscure the sun, and light intensity changes and measurements and so forth and so on, and all this other stuff. Angry seabirds, you don't understand that. That's in a different talk, but we have a sensor network with angry seabirds. They go into their nests at night and they find these sensors in there and they peck at them. Okay, and destroy. So how can you detect these things? Well, the usual approach is to make a model of the normal behavior at a node. If you can do that, not abnormal, not Gaussian, I mean normal in the sense of not anomalous. And then once you have a model of the normal behavior, you can try to classify the anomalies. And there are just zillions of different schemes for anomaly detection. I'm only going to tell you about a couple. Yeah, so these are definitions that we made in the early papers that we wrote about this. So this is a type 1 anomaly. So this picture shows you, can you see it? I guess you can see it. Here's a node, normal data, so these are vectors. So we're assuming that at the node, you're collecting some time interval, you're collecting vectors in order peak 2, 3, 5, whatever it is. So each of these arrows represents one data observation in some dimensional space. So you take it, let's see, oh yeah, I am free, so, sorry, I like to move around. So you have a bunch of, so these coming in like this in time, and you have a bunch of normal ones, and you compress them by representing this bunch of vectors as an ellipse. The way you do is you compute the mean and the covariance, sample covariance matrix, and then you get this black ellipse, right? And at some later point in time, it may happen again. So if you have two ellipses up there, it's going to be the basis of these models. And then at some other time, in between, you will get a bunch of vectors that, you know, are different than the normal ones. So can you see the colors?
Yep.
Yes. Yeah. Okay, maybe my eyes are like my ears. So you get a red ellipse. So that red ellipse goes up there, and so the point is, we're going to do our anomaly detection in this space of ellipses, right? Not in the data space. We also have models that work in the data space, but here we're going to construct a sequence of ellipses, and you'll see in some real data exactly what happens like this. Then the detection will be finding anomalous ellipses. So this is a type 1, so this is an epoch or a window. You can certainly have the same kind of thing for a whole node. So here are a couple of normal nodes. You get those kinds of ellipses. Here are an anomalous node. You get that. Again, you get a different sort of ellipse. And again, the detection space is the space of ellipsoids. Then it could be they have a whole subtree of nodes that behave differently than the so-called normal node. We might have a couple of nodes that produce data like that, and those black ellipses, and you might have a couple of nodes that produce data like that, so these red ellipses. Well, in my picture, you could say, Jim, which ones are anomalies and which ones are normal? Because you have, right? The point is they're different. And so you generate these different kinds of ellipses, and again, the detection space can be a set of ellipsoids. These ellipsoids can live in 2-space, 3-space, whatever space the data is coming into. And we've basically done this up to about 7 dimensions, I guess, using data from networks that monitor electrical use in buildings and things like that. Okay, so here's kind of architectural diagram of the system. So you have a bunch of nodes. Each one is transmitting information, collecting information. We're going to turn, as I just showed you, we're going to turn the information that's collected at each node into a bunch of ellipses, so we get elliptical summaries. From there, we're going to make an image. So I will tell you how we build this image called the IVAD image of the ellipses, because of course you can't see these ellipses with your eyes. They could be an R4 or R5, whatever, and you have no idea how many clusters of ellipses there may be. And what you're hoping is some of the ellipses, the anomalous ellipses, will show up in different places in this image than the ones that you see. So here you see a picture of 3 sets of ellipses, and this image right here has 3 dark blocks along the diagonal. And those dark blocks tell you, this is prior to any clustering, they tell you that there should be, or that you should expect to see 3 clusters in the data. What is the data? The data is a dissimilarity matrix between pairs of ellipses. Well, I'll tell you how to produce this D and how to produce these images in a minute. Okay, so this is the overview of how the system works. And once you have an idea how many clusters to look for, we use single linkage. Single link SL means single linkage. How many people know what that is? Okay, how many people don't like to raise their hands? But that's always the case. Every time I give this talk, I ask that question. Almost everybody puts their hand up. I will tell you a little bit about single linkage clustering in a few minutes, enough so I'm sure you understand it's a very simple method that's useful for relational data. So this matrix D is a relation matrix, even as a distance matrix. Single linkage is used in relational clustering. And so that picture there those are the single linkage clusters produced by clustering that set of ellipses using this scheme. Well, you think, well, Jim, you just recalled the ellipses. It's not true. I mean, it is the actual output. Okay, so what about visual clustering? It's a big topic, one of my favorite topics. I guess I'm going to talk about it Wednesday, some more, or whatever day it is. So visual clustering is really useful and interesting. You're probably used to seeing things like this. You start with a bunch of vectors in RP, and you project them down, for example, to R2, and you end up with some of a scatter diagram or whatever. And get it? But there are many, many schemes to do this projection. For example, this guy Mattins has a program, a MATLAB toolbox of 34 different projection methods, like principal components, random projection, Salmon's algorithm, TSNE, what have you. So you can take high-dimensional data and put it down in R2 and look at it with your eyes, and hopefully learn something about the structure in the upspace by looking at the projection in downspace. It's really not true, because if you take a data set and project it with all 34 of these methods, you're going to see everything from no clusters to 5 clusters to 20 clusters, just by variation in the projection method. But it's done. It's okay to do it. You have to get an idea of what's in the data before you process it, if you can. The other scheme is you may have a distance matrix or a similarity matrix. Doesn't have to be distances. Doesn't have to be square. This one is n by n, not n by n. And I guess Wednesday I'll talk about the rectangular case. I don't remember. That's too far away. So you can easily have data like this, and of course you can start with the data in a high-dimensional space and make a matrix D like this, just by computing distances between pairs of vectors, right? Or you may start out with relational data from the beginning, so you don't have vectors that they come from. Well, what about this? So I tried to show you that there could be a scheme such as this. You see that different rows of this distance matrix are colored blue and red. So it could be that you have a thing that looks like this. So it may be that if you plot, just make a simple, profile plot of the rows of the matrix. The blue ones might have a graph structure like that, and the red ones are different. So you can look at it with your eyes and see, oh, this matrix has 2 kinds of rows in it, or it represents 2 kinds of clusters. So this is the kind of thing you can do with relational data. One of the many things you can do. This particular example comes from R.C. Tryon's 1939 book called Cluster Analysis. If I had known I had longer in time, I would have stuck in some of the history of visual clustering. It's really interesting, and I know it rather well because I like history. When you get old, you like history. How many people here are old? I don't think so. I don't see anybody in this room that was born before me, or even close to before me. Doesn't matter, I guess, really. So anyway, there's lots of different schemes for this. And because you can always convert data, vector data into dissimilarity data, schemes on the right side are somewhat more general. If you start with data on the right side, you can use something like multidimensional scaling to go backwards, but people don't do much of that unless you happen to be in that gang. So that's the first time I used the word gang. How many people are in the machine learning gang? Lots of hands go up. So you understand what I'm saying when I say machine learning gang. That's good. I'm not in it. Why? Because I hate fuzzy sets guys. They hate us. How many people are in the fuzzy sets gang? Just a few. Okay. So I just made a table for you. Visual methods for relational data started in 1873. there's a man in Paris who made an image of 20 neighborhoods in Paris. And it was a rectangular image. And he colored it by hand himself. I mean, in those days, you couldn't make images on the computer. Nobody even knew what that meant. And that's come a long way. And in a longer talk about the history, I would show all of these papers and images from all of them. But I think I'm going to show you one from Zekanowski's paper next, 1909. The guy who invented the minimal spanning tree. He's never given credit for it, but Zekanowski was an important person in clustering, Polish man. And I have one from 1944, Cattell. Well, I believe Cattell invented the term single linkage, so. And I have many others that I won't show in this talk. So when we talk about reordering a relational image or dissimilarity image, it's also called seriation. I can't read that. Can you read that? It looks so dark, you can't read that. It's kind of useless, right? But if you want this talk, I'm happy to give it to you, the whole talk, you know, if you want to put it on your flash drive, whatever, or I can email it to you. So if you just take any matrix and dump it into MATLAB, it'll produce an image for you. Everybody knows that, right? But it doesn't really make any difference how you what intensity or defined or anything like that. MATLAB has many options for making images from matrices. So for example, you could start with this distance matrix right here, a little 5x5 matrix, dump it into MATLAB, you'll get that. Which doesn't tell you much, doesn't really tell you much of anything about the structure that might be in the matrix D that underlies the matrix D. We'll see a different view of that in just a second. The point of this is, can you see any clusters in the image, I of D? And the answer is probably not. You need to reorder the rows and columns of this matrix before the structure becomes evident. So reordering is a big technique. There are lots and lots of different ways to do reordering. I'm going to tell you our way to do it in a minute. But first, Zekanowski, here's his paper from 1909. Of course, in 1909, the only way you could make such a picture was by hand. And I just copied this right out of his paper. Let's see if I can read that. Blah, blah. It basically says, you know, the dark blocks, and they're not nice filled-in blocks, but you can see there are 2 blocks, right? Right? So he said, this is what you should do. 5 manual intensities. Hard to believe, but you know, before you have, I mean, you figure out how to do stuff with whatever you have, whatever tool you have. And the old math guys and the old guys who used to, like, old guys like me, who used to have slide rules. I don't know if Zekanowski probably has slide. How many people know what a slide rule is? God.
Slide rule.
Really? No one in this room knows what a slide rule is? Is it true? When I was your age, that's what you used to make calculations. You had this thing in your hand called a slide rule, and you'd slide the middle part of it, and you could read the cursor, and you trigonometric functions, and you had all kinds of crap. You got good at doing that. Anyway, I was pretty shocked when I found this paper because it was long after. That's exactly my facial expression when I saw this paper. You believe that? Well, then in 1944, I found this paper later, and in this paper only half of the image was built by Cattell. Notice that psychometrica, almost all the early clustering work was either in biometrics, what's now called bioinformatics, or psychology. That's kind of interesting in itself. And the reason I like to show this is I believe that Cattell is the person who invented the term single linkage. Zekanowski was already doing single linkage in 1909, but he didn't call it single linkage. I don't believe it acquired the name single linkage until right here, you can see, right? with or without single linkage list. And I believe this is where the origin of the term single linkage came from. Bring linkage correlations alongside the diagonal if the process successful result in clustering is clearly seen along the diagonal. Okay, so I think actually a person in the UK in 1941 wrote a paper before this, but I've never been able to find that paper about this topic. So, yeah, I just said that. I was even more shocked when I found this, and you'll see why in a minute. Here we go. So now I'm going to tell you about VAT, Visual Assessment of Clustering Tendency, which is an algorithm that Rick Hathaway and I invented in 2002, I guess. So what we made this claim, we claimed in 2002 that the utility of the image in terms of estimating cluster substructure in the underlying object could only be brought to light by reordering the rows and columns of the data matrix, as if it hadn't been known nearly 100 years earlier. But we wrote this up. We took this out of the paper, right? We said we'll reorder D to D star, and when we look at the image of D star, we should see more than we see in the image of D. Yeah, can you hear that? That's us having an idea. Well, you know, after I did it, after I got into the history and found these older papers, I was really surprised to discover that all these ideas have been floating around for nearly 100 years. And in fact, something I can tell all of you is the shelf life of anything you do is about 10 years. You're not studying many things that go back this far, simply because there's so many new things going on that you're learning the stuff that's happening right now. And that's just the way it is. I've discovered over and over, I've been writing papers for 45 years. Many of the papers I wrote 40 years ago have never been heard of. Maybe because they suck, I don't know. That could be. But many of them, they just disappear because your professors are interested in stuff that's happening now. And that's just how it is. So you have to understand that. Okay, so I'm pointing that out here because this is what happened to us. So, we all do it. How many people know who that is? Okay, I'm in the wrong country for that. This is one of my favorite quotes. It's called Hegel's Paradox. And it's about as true as anything you will ever read. Man learns from history, and man learns nothing from history. Yes? This applies directly to us in terms of this paper. That guy is Alfred E. Newman, the star of Mad Comics. Yeah, you know what that is. So here's the VAT algorithm, the original case. I'm just going to put this all up here. So in comes this, by the way, VAT works for only square matrices. There's a co-VAT for rectangular matrices. I'm not going to talk about today, but just to let you know there is one. There's no missing data. We just last week had a paper accepted about how to deal with the missing data case. IEEE transaction TKDE. The asymmetric case, we have a paper about that, what to do if D is not equal to D transpose. So anyway, if these things come in, and I'll just put this up. The point is, you build a minimal spanning tree. There's nothing to be simpler than that, right? Everybody knows what the minimal spanning tree is, I guess. Yes? And we use Prim's algorithm. We use a small variation of Prim's algorithm to generate the minimal spanning tree of the objects underlying D. And the only change is that this line right here, let's see, ij and argument, right? So that's not done in Prim's algorithm. Prim just starts in Crossville. They both just start anywhere in the graph. We find the longest edge in the graph and start at one end of it. And there's a reason for that. If you start at some edge, some vertex in the graph that's kind of in the interior of the graph, this algorithm can go bad. Every algorithm can go bad. Where's the guy with his shirt that says algorithm? Somewhere in the back, right? It doesn't say all algorithms go bad, but it should say that underneath what he said. So, okay, so that's enough about this, right? I think I have a picture about it. The nice thing about this is there's nothing to choose. There are no parameters. You don't have to pick alpha or beta or do experiments or anything. In comes the matrix D. You do the minimal spanning tree. You get the minimal spanning tree. You get the image. So it's very user friendly in that sense. So here's a little data set. Can you see it?
Yeah.
How many clusters? How many people think there are 3 clusters in this data?
4.
How many people think there are 2 clusters in this data? 4. That's interesting. The word cluster doesn't, another word for cluster is a group, right? So if you take the definition of cluster literally, this thing in the bottom right can't be a cluster. It could be noise or whatever, but of course there are many algorithms that will regard that single thing as a cluster, which is okay. You just need to be careful about the definition of the term cluster in the papers you read. Anyway, I guess there are 4 clusters, and we'll see what happens when the VAT algorithm looks at this. If I just start anywhere in this data set, so you can see the blue ones in the bottom, red, green, guess it's green, and orange, right? If I start somewhere and just generate the sequence of edges between pairs randomly, I get an image that looks like this. This image tells you nothing about the structure of the data, right? But certainly this crappy, tiny little toy data set has structure, but you're not learning anything about it. But what you need to do is, they were coming at me. Well, you never know. Anyway, what needs to happen is you need to go through this data set in some ordered sequence way so that the structure of the data becomes evident in the image. So without me even putting this up, you can see if I start down here in the lower left-hand corner, if I start connecting the vertices together, will it ever jump to the other 3 clusters before it connects them all? No. Minimal spanning tree. Think minimal spanning tree.
No.
Right? If I'm building a minimal spanning tree, it's going to connect all the blue points before it goes somewhere else. And then it's going to jump in this diagram, because I know the distance, it's going to jump up, straight up. It'll connect all, the red points. Then it's connect all the green points, and finally it'll pick up that orange point. It's just reordering. I haven't changed the data, I'm just going through it in a different way. Different sequence, so. All right, so there you see, if I start right there and generate the,
What's happening?
if I start right there and generate the minimal spanning tree, you can't see it, but the edges are actually on this picture. Then the image is going to be exactly what you hope. That image. Okay? This is a 10 by 10 block. It corresponds to these points right here, the blue one. Then you have these 2 smaller blocks that correspond to those 2. And this single pixel right here is this guy. Okay? This is the ideal case, of course, but for teaching purposes, it's a good case because you see what you hope will happen. In this particular image, you see the structure of the data quite clearly. You see the size of the clusters, you see how many clusters there are, and everything else. Does this always work? Of course not. Right? No algorithm always works. But this is the idea of that. Well, clusters, yeah, they are. You're thinking, what does it have to do with wireless sensor networks? Right? Well, this is in the middle of it. So now I'm going to talk about single linkage clustering just for a minute. Single linkage is based on a set distance, a standard classic set distance, where the distance between a pair of sets is defined as the minimum distance between a pair of points. One is in one cluster and one is in the other cluster. All right, this is called a single linkage distance. And this has been well known for many, many years. You can go all the way back to the beginning of pattern recognition, clustering, and find diagrams like this. You can do it hard, for example. Single linkage is good when you have chains like this. And it's bad when you have clouds like this. And why is it bad? Because here's what can happen. You're happily connecting these red points, and all of a sudden it finds a blue point that's closer to to the red points than any of the other red points. It jumps into the blue points, and it hooks a few of them up, and then the same thing happens again, jump back to the red like that. So a single linkage is built for chaining type structure, and it's not so hot for cloud-like clusters. Okay? Just the reverse of k-means, for example. K-means is no good. If I run C-means or fuzzy C-means, whatever, on the upper data, on the picture in the upper set, it'll cut it in half this way. Wrong. Yeah, I guess it's there with it, right? Yeah. In the upper set right there, if I have a bunch of points like this, k-means will cut it like this, which is also wrong, of course. So you should understand, I guess that, or you do understand, I hope, the success of your clustering algorithm depends to a large extent on the distribution of data. And of course, if data is higher than 3 dimensions, you have no way of knowing the distribution of data. And that's the whole point of using these imaging technique, is to try to look at the data in the up space. Okay? That's what that does. It looks in the up space, not the down space. Okay, so here's 100 points. Where do they come from? They come from a sample of 1,000,000 points, which I'll show on Wednesday in your conference talk, I guess. But you're not going to see there's 1,000,000 points today. And, okay, go back. So if I just take these 100 points and I make a Euclidean distance matrix, so it's 100 by 100, right? Symmetric. So I just compute the Euclidean distance between pairs of points in these two-dimensional points right here, and make the that image. Exactly, that image. I get this. I count the number of dark blocks, and I see that it's 10. And this picture is 10. And an interesting thing is, if I ask you how many dark blocks are, you might be tempted to say, oh, 1, 2, 3, 4, maybe 5. Right? So one of the things that you get out of these visual techniques is you get the idea that in this big rectangle, there's actually a substructure with 5 smaller subblocks in it. You can see stuff like that. We've done a lot of mammographic images where you can see the substructure of that type of image this way. Okay? Anyway, in this, if you think there are 10, I do think there are 10. I've looked at hundreds and hundreds and hundreds of these images. If there are 10 blocks, then you have 9 edges to cut in the minimal spanning tree. Oh, that first one up there missed. This drifted. 1, 2, 3, 4, 5, 6. Can you see it?
Do you want pointer?
What is that?
Pointer.
Does it work?
Yes.
I don't know.
The other way. Turn it around. Turn it around. Okay, yeah. There is a button.
Turn it on for me.
You simply click here.
Ah, so clever. Is this Bulgarian?
Chinese.
Yeah.
You can hardly, I mean, with the projection system we have, you can hardly see there's two subblocks there. On my computer, if you go look at it, you can clearly see them. Okay, so anyway, you have to believe me, there are 9. Right? Why? Because my chart says there are 9. So you say, okay, great. There must be 10 clusters. That means I will go back through the minimal spanning tree backwards and cut the 9 longest edges. And that will produce for me the 10 subtrees in the graph that are the clusters that correspond to the picture. So that's what I do. I think I actually have the minimal spanning tree here. Yeah. So this is a picture of the minimal spanning tree on the 100 points. And you just cut those edges, you just cut so single linkage is going to make a back pass through the data and just cut the green edges, right? But this is a simple thing. Single linkage, it's a nice algorithm. I always try it when I'm doing a new clustering problem. And there's the partition you get, and it's pretty good. That's a single linkage partition generated from the 100 points. If you run k-means on this 100 points, you won't get anything like this. K-means has got its own problems. They all do. We all do. Okay, so there are also cases where VAT fails, of course. So here, can you see that? Wait a minute. Oh, I didn't learn to use this well enough. Right. Can you see the data set? Two ring, can you see there are two rings?
Yes.
Two clusters, right? Right? Two clusters?
Two clusters.
Yeah, why not, Jim? Put your hand up. What Jim wants you to do, put your hand up, just do it. Put your up down. But if you run VAT on this thing, well, if you just look at it, yeah, if you if you just start anywhere, and if you just take the matrix that corresponds to the Euclidean distance matrix for this data set and dump it in MATLAB, you get that, right? Which tells you nothing about the two rings. And if you instead do if you do VAT, you get that, which also tells you nothing. Basically, it's got some kind of, I can't remember how this works, right? This has got, you can see there's something going on, but you don't know what it is, right? So this image is really not much more informative and any more informative, so neither one of these is really useful to you in terms of understanding what's in this data set right here. Okay, so can we fix that? We sure can. What do you see? Nothing. Well, IVAT, I means improved VAT, of course. I mean, it's not like Apple owns, I wish Apple did own IVAT, and I'd be rich. Unless I lived in Ireland. I just came from Ireland yesterday. Ireland's in a tizzy because the EU just told Apple they had to pay Ireland $13 billion, right?
Yeah.
We in the US want the $13 billion. So, yeah, enough of that. I don't want to get started on that. So. Anyway, the point is what we just saw is the VAT image often generates the wrong things that aren't so useful to you. So we discovered a fix for this by reading papers about spectral clustering, which is a misnamed thing. How many people have read papers about spectral clustering? Not so many. None. None is not so many, right? That's a fuzzy term. Okay. Well, so the idea here is we're going to transform the distance matrix D into D prime using a geodesic distance. This is all past short of pair problem, computer science. I'll just show you a picture. So here I have two vertices in some graph, and I have an edge or a distance between the OI and OJ, right? And DIJ. The question is there any other paths in the graph that will take me from I to J or vice versa? So maybe I could find one that looks like that. So that's a different path from I to J. Well, I go along that path and I find the biggest distance along that path. And that distance happens to be M1. Well, I try to draw it so it's M1. Then I might find a different path. Right? I find the longest distance along that path. And that's M2. So maybe those are all the paths between I and J in this graph. So now what I do is I just look at the values I got along each path, and I take the smallest value I can find, and that's the min of the maxes, and I replace the original value of Dij if it's not the smallest one with the one along a different path, and here that happens to be M1. Right? Does everyone understand what's going on here? It's just feature extraction. You understand. Right. Okay. Everybody who doesn't understand, put your hand up. Nobody puts their hand up. It's okay. You understand what I'm saying? You're in a graph, right? You're in a graph, and you can go directly from vertex I to vertex J. You can have a distance between the 2 points, or an edge weight. Basically, can I get to it some other way by going some intermediate vertices? You know, like in the picture. Yes, I can go a different way. You go along that path, and you find the longest link in the chain, the longest edge link in the chain, longest distance. You look at all the paths that go from I to J, and along each path you pick out the longest distance, or the longest edge, right? And then you just take the smallest of all of them. And if it's smaller than the original direct link distance, you just replace it. So all you're doing is taking the matrix D, the original distance matrix, and changing it to D prime. Now, in a big matrix, you might only replace half the elements or something like that. Okay? Well, you're all kind of thinking, oh, it's lunchtime, Jim. And we're not there yet. You're really thinking, what the hell does this have to do with, wireless sensor network? So anyway, this distance is well suited to single linkage and to back. Let me just show you some pictures here. Oh, well, first I have the algorithm, so there's nothing new going on here. And I know that I'm just flashing these up and you don't understand how this works. It's okay. This again is a very simple, this is just, what you do is you just transform D into D prime and then you do VAT. But this is a recursive implementation. I have all these papers you want. Again, there is no threshold. You don't have to pick anything. There's no choices to make. It's nice. The original way we did this was ON cubed. But the recursive, well, that happened. Let me go backwards. Right. The iterative implementation of this extraction technique is ON cubed. But if you do it recursively, you can drop it to ON squared, which is good. So here are some pictures, I guess. Synthetic data sets. Well, I just put them all up here. So, everybody can see them? Yes? So these are all two. Yeah, did it fail? Your battery, no, it's still there. So how many clusters? Two, right? But if you look at the VAT image of it, you can kind of see there are two clusters. If you look at the IVAT image of it, you can clearly see that it suggests two. So let's look at a harder one, if I can find it. How many clusters? Three, right?
Yeah.
Okay, if you look at the VAT image of that thing, which we saw a crappy VAT image before, you can see nothing. But if you look at the IVAT image, not only can you see there are three, this little smallest set of pixels corresponds to the center cluster, and so forth, medium and large. But you can't tell it, but this is, there are three different sections of the helix here. 4 lines, clear, nothing. 5 clusters, nothing, pretty clear. So you can see that IVAT really improves what you see with your eyes in most instances. Not every instance, but in most instances. So nowadays, we use only IVAT, we being the people who do this, because it works so much better. And if I was giving a different talk, I have lots of examples and blah, blah, blah. But I was trying to get back to wireless sensor network. And now I do get back to wireless sensor network. Remember I said we were going to do detection pairs of ellipses. If I asked you, do you think there are any papers out there that tell you how to measure the distance between a pair of ellipses? What would you say? Would you say yes, there's lots of papers? Well, if I ask the question this way, I want you to say no. Right? When we started doing this about 2011, I thought there would be lots of it makes it simple. It sounds like a simple question. You would think the math gang, how many people in the math gang? I'm in the math gang. Okay. I would have thought people in the math gang years and years and years ago would have written lots of papers about how to measure the distance between a pair of ellipses. It's not true. It's not true, and it's not clear how to do it, so we invented a bunch of different ways to do it. 4 to be exact, only one of which really works well. So a strong similarity measure between a pair of ellipses, just a strong similarity measure. I don't know if you can read that. So EI and EJ are ellipses, ellipse I and ellipse J. Similarity between them is, in between 0 and 1. It's 1 if and only if EI equals EJ, the ellipses are equal. And it's symmetric. It's a weak similarity measure if that one property only goes one way. So what are the important properties for pairwise similarity of ellipses? You want to measure the similarity between a pair of ellipses, what we're going to look at?
Overlap.
What?
Overlap.
Overlap? How will you measure that? If you don't have the ellipses. Okay, well how about the means? The centers of the ellipses, certainly. And how about the shape? Right, you know, you can adjust the shape of the ellipse by changing its eigenstructure of its sample covariance matrix, right? The shape, and you have orientation, which is given to you by the eigenvectors of the inverse of the covariance matrix. It seems like the three important properties for measuring the shape, measuring similarity of parallel ellipses are location, central tendency, shape, and orientation. That's what I believe. So I'm just going to flash through these. I know you're not going to have time to appreciate the equation. We want to move on to the application. So I invented this one, compound. Here's the function, right? Just show you what it's got in it. And I proved this theorem. And I thought, oh, this is going to be the perfect measure of similarity between a pair of ellipses. You see it in both shape, means, and orientation. And it seems like a natural measure. It was probably the first one you invent when we were trying to do it. It turns out it worked crappy. It's like really the worst of the four we looked at. It's shocking me, but it's okay. I've invented other stuff that didn't work too, so what? And then Lawrence Park, the guy in Sydney, he invented this one, which is really a strange one. And you won't understand these formulas unless you get the paper and read it. His idea was, we'll transform both ellipses, we'll measure the energy it costs us to transform both ellipses into a common space. So this matrix R is a rotation matrix. You can do this. This optimization problem is not a trivial thing to solve. And we proved, you know, Lawrence and I proved that this is also a strong similarity measure, but it also doesn't work very well. Then, of course, in the literature you can find this one. This is not really offered to the community as a measure between pairs of ellipses, but you can use it as one. It involves the three elements that are important. The Data distance, been around for a long time. It measures the distance, supposedly measures the distance between a pair of p-varied Gaussians. Okay, so we included that in the study, and then the big one, the main one, was invented really by Mastagi in 2010, I guess, which is called focal distance between a pair of ellipses. This is really clever, and it really works nicely. So let me remind you, from your high school days, or in Bulgaria, it's probably your junior high school days. Why do I say that? My friend Lucy Koncheva, how many of you know who that is? Okay, she's a Bulgarian person who's a professor in Wales now. She visited me and we wrote some papers years ago, and then she moved to Wales, and she took her kids. She had a 14, 12-year-old kid at that time. Her husband wanted to come back to Bulgaria, but they'd been there 1 year. I said, well, Lucy, move back to Bulgaria if that's what you want to do. She said, my kids, if I took them back now, would fail out of school because they've missed 1 year of education in Bulgaria, and it's so much better than education in Wales, they would be lost. It's an interesting thing, actually. There's some real differences between education in the U.S. and U.K. and here. I told you this story earlier, right? You get to hear it twice, and you didn't want to hear it either time. There's a 2D ellipse, just this, ellipse from plane geometry. And I guess probably you may not remember, but there's a couple of different ways to generate it. T, let's see if I can make this work. Right? Even though it's not really a radius, it's called the effective radius of the ellipse. And you have a parametric family of ellipses as you change the value of T. You have an infinite family of ellipses, right? But for a particular value of T, you can get this ellipse. You can get the eigenvalues and the eigenvectors that go with this ellipsoid. All right, and once you have them, you can compute the foci, F1 and F2. It's just a simple formula. Here's the eigenvector that goes with the bigger eigenvalue, and here are the minimum maximum eigenvalues. You get this pair of points right here, F1 and F2. And once you have the pair of points, you can get the focal segment. That's just that little line segment in between F1 and F2. How many people remember that from high school? Wow, that's a pretty good show of hands. How many people learned to do it with a string? Make one. I actually still do that when I'm woodworking. Okay, so this is the basic idea. Now, what has this got to do with the pair of ellipses? Suppose this is the heart of the elliptical summaries anomaly detection algorithm. Well, they have two ellipses in 2D. So I get the focal segment of each one of them. What can I compute? Well, lots of things, but what we did compute with these, let me just put these up. Delta 1, delta 2. So you start at either vertex, you compute the distance to the two endpoints of the other focal segment. So you can do it both ways, of course. So you can get these four numbers, right? And then the genius idea really was, wouldn't there be a better number you could get if you could take this thing? He said, what we're going to do is we're going to start at this, we're going to make the orthogonal projection of this focal segment down to the other focal segment. And if it hits it, we use that distance instead because it's a smaller distance. All right? If you take the longer focal segment and project it up, you miss the short one on both ends, right? But if you take the short one and project it down, you hit the focal segment on both ends. So that was his idea, and it turned out to be a really great idea. So, this is a rule, or whatever you want to call it. If the orthogonal projection of a foci lands on an opposite focal segment, we'll replace one of those distances with the, with the smaller distance. So in this picture, E and F would replace delta 3 and delta 4. Now you have these four numbers, take their average, define that as the focal distance between this pair of ellipses. Okay? I mean, when you see something like this, you think, what a great idea. That's what I thought when I saw it. I know I've taught math for 40 years, and I know when you teach a class to show how a theorem is proved, I know the people in the class think, but how did the guy think of doing that? Right? After you've taught math for 30, 40 years, you know how the guy thought of it because you've done it over and over and over. And you can pretend it's easy to see, but I know it's not easy to see. Okay, so I look at this and I said, God, Masood, this would be great. Well, I didn't think of it, Masood thought of it. So let's see how it works. When P is the number of dimensions of the vectors that you're collecting in this wireless sensor network, greater than 2, what do you do? Because this is well defined only for plane ellipses. Well, you do I guess we would say the obvious thing, you just do it pairwise for each pair. You order the eigenvectors and the eigenvalues of both of these ellipses. It will be P of them, right? And you just take the first pair, the second pair, and it's up to P minus 1. So for each pair, they are plane ellipses, and you can just compute the focal distance, and then you just take the average. So we prove a little theorem that this focal distance is focal distance pseudometric on the base of the union of all the ellipses crossed into itself. Okay. Okay, here's a little quiz for you all. Which pair of ellipses is most or least similar? Let's put them up here. There's 5 cases. How many people think the first? So I'm going to ask you for a show of hands. How many people think the first pair is either most similar or least similar to the rest? Second pair. Third pair. Are what? Most similar?
Yes.
Does anybody like the fourth pair for most similar? Really? Fifth pair. That's good. Fifth pair. Most similar? Couple of hands. All right. How about least similar? First pair. Second pair. Third pair. Least similar? Okay, you're kind of contrarian. Good, not bad. Fourth pair. Fifth pair. Okay, so if you were watching your colleagues here in the room, you would see that there were votes for almost all the cases, right? So if we humans can't see it, right? How would you expect a computer to get it right? So we have these 4 measures maybe you'll be surprised, maybe not. I just put them up here now. So these are values of Bhattacharya coefficient on these 5 pairs, the focal distance, the energy, total transformation energy in my, and you know, this one on the bottom is the one I invented. You can see it, right? This compound symbol basically tells you nothing about the 5 different cases, whereas the first, you know, the first two, these two here, they have the same shape, these two graphs, which is kind of an interesting thing. And I've always conjectured that somehow you could prove a relationship between the Bhattacharya distance and the focal distance, but I haven't figured out how to do it. So those of you who like math problems and want to do a PhD in math can do that. You can work on that. Be good. All right? So let's see what their votes are. Obviously, these are the least similar. Where it is these two right here. And the most similar, according to these measures, is this pair right here. I know that most of you think this is the pair that are most similar because they're identical except for their location is different.
But the center of the fifth pair is the same.
That's right. And these they are. And that's what you learn in this diagram. As far as these, I'm not saying it's true, right? But I'm saying in terms of these measures, the measures prefer to call things similar that have the same means. This is a first order tendency, right? And the shape and orientation is second order tendency. It comes from the covariance matrices, right? So that's what you see. I already said this, compound energy is terrible. I said this too, and I just said this. And this is pretty consistent with the way we think of real things in statistics in a statistical sense. The most important property of sets of numbers is their central tendency, right? The first thing you want to know when you look at a Gaussian distribution is where is the mean? Where is the central? No matter how many dimensions it's in. And the second most important thing is just like a Taylor series. The most important term is the linear term, and the second term is the quadratic term. That's what shape and orientation are all about. So it's kind of cute. So now we come to some anomaly detection. So first I have a set of, I can hardly see them. These are 30 ellipses. This is synthetic data, of course. Then we just stuck into 3 clusters, right? 3 clusters of ellipses. Before I do any clustering, remember now, we're pretending that we can't see these ellipses, and we can't see them in the real case. Before doing any clustering, there are several ways I could get an idea of how many clusters to look for. For example, there's an analytic method due to a Russian fellow in 1988 who published a paper that said and proved that if you have a distance matrix with block structure, and that's the type of matrix that these IVAD matrices are, hopefully, block structure, and there are C blocks, the first C eigenvalues will be much bigger than the remaining eigenvalues. So this is a plot of the eigenvalues, and you can see there's a break. I guess you can see there's a break in it. So this is Euclidean, the dissimilarity matrix generated by the focal distance, right? Its eigenvalues, 3 of them are big and the rest are small. Or you could have a look at the IVAD image, and the IVAD image clearly tells you that it thinks there are 3 clusters of ellipses. This happens before you go looking for the clusters. And after you get, afterward, if you do single linkage, there's a heuristic. There's a heuristic based on single linkage merger distances that says look for the knee in the graph of the merger distances, and that happens right there at 3. So all these methods, before clustering and after clustering, agree that there should be 3 clusters in the data. Then you go do the clustering, and you get this single linkage 3 partition, which I showed earlier. Actually, it was on the architecture chart, this example. We did many of these, but I have some more interesting ones coming up. So here's an example of the wireless sensor network at the Intel Berkeley Research Lab. IBRL data has been around for a long time. You can get on the internet. I think I have this. Yeah. this is 12 years old now. The two things collected at each station in this lab are temperature and humidity. And sampled every 30 seconds for 4 hours, so that's what the input data looks like. So we took each of those and built an ellipse. You're going to see node 17 on the next chart was known to have low power, so that, you know, the collection was drifting. So here's the. This is a picture of the 54 ellipses. I don't know if you can see this very well. Can you all see that there's one ellipse that's anomalous? Yes. Right? You can see it, right? And that's that node 17. You can't see 17. It's actually on this chart. And if you do the analytic eigenvalue method, it says, you can't see that, 2. But happily it says 2. And if I do the IVAT image of this matrix, right, you can see this, there's a little, yeah, there's actually sort of a little, there's a second ellipse in this picture that's somewhat anomalous, and I believe it's this long one. Then post-clustering, same sort of thing. And then here's the single linkage output. So the anomalous sensor in the sensor network is represented by this anomalous ellipse, and this ESAT scheme sees it through single linkage clustering, and you know, we code it so you can see it. Okay. So this is the basic idea in this particular model. Yeah, so how many clusters of ellipses here? How many people say 2? 3? 4? Okay, so I got votes for all 3. Yeah, I mean, it depends on your point of view, I suppose. Certainly there are 2 underlying clusters of ellipses, but each of those underlying clusters has one anomalous ellipse. You can see that, right? And so, what does IVAT see? Well, it sees the same thing that you see. These 2 single pixels here hanging out, they correspond to the 2 anomalous ellipses. Okay, so that's really, this is a nice picture actually, because this picture reveals what you see with your eyes. Now again, since you can see this, since this is 2-dimensional data, right, you say, yeah, big deal, who needs the image? Well, but we can generate the same kind of picture in R4 where you can't see it, but IVAT will still see it. So that's the point. So, yeah, the first couple times I put this up, people said, well, why don't you use fuzzy C-means on this data instead? So I said, what? Like what data? So what you have for these ellipses, for each ellipse you have a mean, a center, right, and a covariance matrix. You could cluster the means, for example. If you plot the means, this is what it looks like. You can see that there, I mean, I don't know if you can see the colors, but it's cut, right? If you run k-means or hard k-means, fuzzy k-means, possibilistic k-means, you're going to get C equals 2 clusters. That's because it's driven by central tendency. And on the other hand, if you plot the covariance matrices, right, the 3-dimensional covariance matrices have, right, they're symmetric. So only have 2 diagonals and 1 off diagonal. Again, you can see only 1, 2 clusters. So if you run a numerical clustering algorithm on this data, you will get the wrong, what you won't get. You won't get what you want, which is some information about, about this, right? The anomalies are lost. So there's a lot to be learned by looking at different representations of data. Okay, so now, what is that? That's a fish I call that's my dock right there. I caught this fish in my backyard 2 years ago. And then I ate it, of course, the red fish. Nice enough fish. So now we're shifting gears, right? So we're kind of done with the ESAT model, but I want to just tell you about a couple of results from other papers in case you were interested. This is one of the other papers. So this is about streaming data with incremental IVAT. I haven't told you how incremental IVAT works, I'll do that now. So one of the big things in the States anyway now is streaming data. How about here in Bulgaria? Yes? Yeah, big data is the big thing. And one of the ways you can attack big data is instead do it one at a time as it comes in, rather than let it grow like a blowfish or something. Right? So there's a whole lot of pushing now about streaming data. And so I thought, well, why don't we have a streaming IVAT? And this kid, she's a kid to me, Dheeraj Kumar is like the world's expert now on that. Right? He figured out a way, given a graph, an end nodes, you're handed one new vertex, so of course you have n new distances. He figured out a way to pull out the worst edge and replace it with the edge with the best edge, so that you don't destroy the minimal span tree. But you think that's an easy problem, but think about it. Anyway, we figured out how to do it, and we wrote this. We had this paper. There's 29 algorithms in it. Little boxes of algorithms. I said, Dheeraj, no referees after they see 4 of these who say, the hell, I'm tired of this, and just reject the paper. It's really a long paper, 41 pages, I think, in the transactions of HCM transactions of mathematical software. It's a really great paper. It's not this paper, this is a different paper. But anyway, I have some Heron Island pictures to show you about it that are interesting. So how does this work? So here's the basic idea. Here are 9 points that have come in, time 1 through 9, coming in. And you can see that if you saw all 9 of them at the same time, you would see the red ones and the blue ones in 2 clusters. But that isn't what's going on. So you pick, just pretend that you pick a sliding window that's 7 by 7. You see the first 6 points, you see one cluster. When you look at the image, well, it's one big square with a bunch of subsquares. Okay, so in comes the 7th point, the first blue point comes in, and the image will look like that. These are actually real images, not fake images. They come from this data, which is good. Yeah, it shows you that when this, only 1 pixel represents 0.7. Now 0.8 comes in, so 1 has to go out because the window is only 7 units long. All right. So x8 is added, the second blue point, and x1 just in the time sequence deleted, and the image looks like that. So that's what you want, right? The pixels grow there, and it just keeps going like that. Okay. Now, we've done this up to about the window size of about 7,500, and I have a movie to show you in a minute that's close to that, and it works pretty. It's really pretty clever. Works really nicely. Right now we're doing some neuron spike images with the University of Toronto neuroscience gang using this scheme, where you can look at the waveforms that come off of slices of people who have epilepsy, actually. It's really an interesting application. So this is something that's going to grow. But it chose not to show you that here. So here we have Heron Island. Let's see. This is a picture. You can see. So this is a picture of Heron Island. It has a bunch of weather stations on it. I didn't show you a picture of Australia. This is north and east of the northeast coast of Australia. It's about 50 or 60 miles offshore. All right, this is a weather station, and here we're collecting TPH, temperature, pressure, and humidity at each of these stations. You can go to the internet and get this data. And the interesting thing that happened is there was what they call a cyclone in the southern hemisphere. We call a hurricane. You don't get either one, right? Here in Bulgaria. You ever have a hurricane in Bulgaria?
No. And we are really
What
happy.
do you have?
And we are really happy.
Forest fires? Floods?
Forest fires.
Yeah, it was some
There are earthquakes.
Invasions?
Yes.
Yeah, we have that too. And moron Donald Trump says he's going to stop that. He won't. We don't want to go there, right? Anyway, each of these sensors in this network, and they are a wireless sensor network, collects this data, right? You can go get on the internet if you want. And there is an anomaly. This is 30 days worth of data, right? You'll see that there is an anomaly. So so first I have these static pictures. So here's humidity and pressure. Can you see it? Surely you can. So these are the ellipses that you generate. So you get, right? Surely this, remember now, we're not looking at the data, we're looking at the ellipses. Right? You can clearly see there's an anomaly.
Yeah, I have a question. When you generate the ellipses, what is the discrete of time? I mean, what is the discrete of time? I mean, when you have a value, so it's like 1 hour.
This is 1 day.
1 day.
1 day.
Okay. So each ellipse is.
Each ellipse is 1 day.
It's 1 day.
There are
Okay.
30 ellipses.
Okay.
Yeah. So let's see what happens here. Here's the iPad image of that, and you can see if you can see, right? This pixel right here corresponds to that red ellipse, and I believe this pixel right here corresponds to that real long one. Right? But notice that this pixel is a portion of this huge structure here, which is all of these ellipses except this one. And when you do signal linkage on the ellipse, on the focal distance matrix of the ellipses, you get that. If you look at temperature and pressure, you get a similar kind of thing that looks like that. If you do temperature and humidity, you also have an anomalous ellipse, or most obvious anomalous ellipse, and it's again seen in the IBAN image, right? And you get something like that. But the important point is, these two ellipses correspond to humidity and pressure and temperature and pressure. And what happens when you get a hurricane or a cyclone is, what happens, what's the big parameter that changes?
Pressure.
It's pressure, right? The barometer drops like crazy when a hurricane's coming your way. So you see the pressure is not, right? So the pressure is missing here. I can find this, right? This pair of variables, there is no pressure, and this anomaly does not correspond to the cyclone. It's a temperature anomaly that shows up on a different day. So the first two are the cyclone Hamish, ellipse number 7, day number 17, and the third one is day number 13. It's a different day. But that's okay, it was an anomalous. Yeah, I mean, the weather was anomalous that day. And now, now I have a movie of this that, unfortunately, I can't control the time of it without getting out of here, so let me do that. And my old knees are kind of creaky. First, let me show you. So what you're going to see is, you can see ink like that, and deck like that, working as this. So this data is coming in like this, one at a time. Let me just show you, rather than run the whole movie, let me show you, I'm going to page through it, but I will run part of it. Well, I think I'm going to page through it. See on the right, you see the image growing. In comes this is a cyclone actually, you get a red set of red pixels there, and so forth. So I just run a little piece of it. Say from about here. And now, if you look at the dots, the blue points are coming in. They're classified as normal. And this thing down here compares the average distance that's been seen to the distance of the incoming point. Right? And you can see over here, you can see this right now it thinks there are two clusters. What happened? Did it stop? It's still running. No, it's still running, I guess. Right? Now it goes back to thinking there's one. So what you're seeing is you're seeing the evolution of the IVAT image on the right side of the screen. And we should be hitting this anomaly pretty soon. First one is still running, getting bigger. So we have an now I can't see it myself. It's almost there. There. Okay, so then comes this is probably the temperature anomaly first. you see there's a little block of red pixels here, right? And they will stay red because this piece of the data set is displaced from the other piece of the data set. Okay? And as it keeps, so this was the 13th of March. And see right here, right now, it thinks those are anomalies, but now it changes its mind and puts them back in the normal model. And now comes the cyclone that's coming in now. Here's the cyclone on the 17th of March. And you can't see it too well, but now there are two red blocks colored down there. And this thing will just run all the way to the end with nothing else changing. Because all the rest of the data that comes in will be put in this big blue cluster, which is a normal model. So this is the way IncIVAT works and DecIVAT. And this is a very useful technique in neuroscience, neurosurgeon at the University of Toronto. Just hook this up to an actual human brain, right? And they, they have these electrodes, right? And they hook this up. They hook a computer to some electrode, right? And they can watch the evolution of, neuron firing from single neurons. I mean, to me, it seems incredible. To you, you probably think, sure, anybody can do that. Anyway, that's the way this works. And then, so I can get out of there. Go to the next one. Okay, so this is a video from a different paper. And again, not only, like I said, we started this in 2009, I guess, and we're still working along on it. This elliptical submarine model has evolved into this thing. Fuzzy rules for anomaly detection and data streaming. You have a famous countryman who's well known for the competitor version of this. How many people know who that famous countryman is? Okay, his name is Clément Angelo. And he's in the UK. And so, where's our man? Joseph said, he's not really a Bulgarian anymore. He's an Englishman. I said, really? So that means Dimitar Filev, who's in the US, my friend in Michigan, he's an American now. But I don't think that way. I mean, he is an American citizen for sure. Anyway, Angelov and his students in the UK have developed a competitor system, and he sells software, and he's trying to make money with it. Manuals and stuff like that. If you want ours, we just give it to you. Okay? Professor software. I have a real short video. Actually, and I guess I can just run it like this. Is he gonna run? Maybe I just do this. Or I don't have to. There it goes. So this is a data set where you have two modes. Here's a data set with 10 Gaussian distributions that go along in a chain. Just so you see the evolution of the ellipses. And there's one more data set, which is a wireless sensor network, the light genetic data, which is, I think, in Switzerland. Okay, so this was a model that came way later than the ones I talked about earlier. These days right here were snow days. This is up in some mountain pass, I guess. These days were clear, nice days, and these green days, again, were nice. Time goes from right to left here. It was snowed in this regime right here, so it's okay. Okay? So this is just one snapshot of the whole paper's worth of stuff. I think we're actually, now I have to go back to this other stuff. Do it. You say, what a great word to see one, right? I've been sitting here forever, and now this guy's going to quit talking. So we actually have more than 3 kinds, and different people define anomalies in different ways. But I talked about type 1, type 2, and type higher order anomalies briefly. We had 2 models for detection, although I didn't talk about the data capture model. We have a model that does this without converting to ellipses. It doesn't work as well. 4 measures of dissimilarity, I talked about those a little bit. this is how the data capture model works. And again, I didn't give a talk about that today. I have a whole talk about that, but I just couldn't pack it all in here. And the visual model, this is one I did talk about. Right? We use elliptical summary. Why use ellipses? Well, because ellipses are like the first two terms of the Taylor series, and because Gaussian distributions, right, are well modeled by them, of course. Now, not all data sets are Gaussian, but many data sets are assumed to be Gaussian, and many algorithms are tuned up for Gaussian data. You have to do lots of things to do. Yeah, we have done this. It's solved for 3 dimensions, and we have data from the neuroscience guys for 64 dimensions. So we will be testing it on that soon. We should compare the visual method to other methods. So I've already done that with Angelos' method. And kind of kicked his butt. Right now we're working on streaming cluster validity models in Australia, which I haven't talked at all about. Cluster validity, that's another talk that you won't hear today. Yeah, and streaming data situations. So the big things now are big data, which I'll talk about Wednesday, and streaming data. And now, I think we're going to see, you're looking at this thinking, what? That's my son Eric. And this is a soccer team I coach. I, an American, coach a soccer team, and I love soccer better than any other sport. And I coached soccer for many years. I never played it. I actually coached at the university level. So anyway, he just wrapped it up, so we will. So, time for you to wake up. I have many pictures of myself that look like this. Something can happen. Yeah, it's funny over. This is a picture of me and my lovely wife who's over here in the hotel. See, you can see nice thing like this. This is the last motorcycle I had before the hurricane. I never bought mine after the hurricane. I should have done it. I already told you this. If you have questions now, I'll try to answer them. Oh, sure, you sneak back in when you know the talk's over. And there's my email address. Happy to say, if you give me the papers of the talk right now, if you want to bring your flash drive up here, or if you want to email me and say, send me paper X or send me the talk or whatever, we have to do that, whatever you want. Okay? Now you can clap.
Any questions?
Uh-oh.
What if you have 2 clusters of data that are very similar?
Why are you holding your hand out like this then?
Okay, they're similar, but they're in different positions. Which is the anomaly? Is it possible to
Similar
detect
mean? Well, what does very similar mean? What do you mean by that?
Then, let's say they're exactly the same distribution,
Yeah?
but they're
Separated.
Separated, yeah.
What's the question about them?
Because they're... Okay.
No, I understand the data set. What's the question?
The question is how you can prove which is the anomaly. In
How
case
you
like
can
this. Prove which is the anomaly. Like your normal work world is this set of points here.
Yeah, okay. Yeah, so I showed one picture that had 2 nodes with black arrows and 2 nodes with red arrows, right?
Yeah.
Like that. You can say, well, which one's normal and which one's abnormal. I mean, it's a matter of definition. You, the human, has to do that. But this is the way it is. Sorry. Maybe they're both normal. Look, you have these processes where you switch from one mode to another mode.
Yeah.
Actually, the video I showed right at the end showed one cluster in the bottom and another one. So you have this switching regression model, right? And many time series are like this. No, neither one of them could be called normal or abnormal. They're both normal in different pieces of time. But they can have anomalies. There's 2 clusters that are similar, but there's one point staying over here. Right? It's the anomaly you're looking at. Next question.
Any other questions? Come on.
Yeah.
I'm wondering, because you mentioned ellipses comparing to circles. What is the, what's the advantage of ellipses? Is it the
The
accuracy?
advantage of ellipses is you only have to store two things. And you only have to transmit two things. You have to store the mean and the covariance matrix. Right? So you can let the thing run for an hour and get one mean and one, or whatever processing time you have. If you're going to share the data with other nodes, you only have to share is the mean and the covariance matrix. Much cheaper to transmit than send every data point. Right? It's not a method I invented. There are many clustering algorithms that do this. Right? Even has some kind of a canonical name invented by Bezdek and these guys. Cluster statistics, they're called. Right? So instead of worrying about 1,000,000 points in R7, you just get the mean of the 1,000,000 points and the covariance stuff together. So it's a matter of economy. Next question? Next question is the final one. Can we go get it? Sure.
More general, how you may define what exactly causes the anomaly. For instance, no, I have a lot of data coming, and I have a model that I don't know exactly. I create a model, and then the model, when I a training model, and then when I test the data, it found that there's something normal.
Something went wrong.
Yeah, but what causes this?
Now you're asking me to have an explanation facility attached to the model, right? If you have a fuzzy rule base, you can sometimes generate semantics that go with the anomaly that make a description of it. I could show you in a different talk if you want me to do that. Do you? The rest of the people in the room saying, no, say no. I want to get up and leave. Look. Okay, if you're looking at seismographic data, you have seismographic data, go bang like that, right? What causes the anomaly? Well, right? Bang! What causes the anomaly? Well, it's a tremor in the earth. You know what causes it, right? Some physical system, there's only one kind of anomaly you care about, and it's weather station data. There's more than one kind of anomaly, and unless you know what happened physically, you don't know what caused the anomaly, right? So, I did not cover any explanation facility, but I have other charts about that type of question. Maybe most people want to leave, you want to hang out, I'll show it to you. Okay with me? Right? You understand my answer? Let me try this again. Bang! Look at this, the youngest kid that ever joined the IEEE, right here. He has a license single. I never had a kid this size come to the talk. And the oldest person ever came to one of my talks? Me.
I wanted to ask about the types of data that you make data analysis on. You mentioned that there are relational and dimensional data. Are there other types of data that you can do analysis on?
There are other types of data, but not numerical data. Sure, there are lots of things that are data that aren't numbers.
So these are the only two types.
But you can represent almost everything with numbers.
It comes from me. It's music in my brain. Sure, there are many things that are called data nowadays. The word data is a pretty general term now. And there are many kinds of data that are non-numerical. In essence, I have talked about it, and I've worked on in my lifetime on all numerical data. Either vectorial data or relational data. Okay? You can say, what about an image? Well, an image is a bunch of numbers, but you can deal with images like they're images, not bunches of numbers. So there are lots of things that are data. Voice, Did I answer your question? Not the way you wanted me to answer.
No, it's okay.
I actually have a definition of data that encompasses, 20 or 30 different types of information that are collected. you know, that aren't represented by numbers. Okay, colors. I mean, think could be, you know, like eye colors. That's the data about your eyes. You can change it into numbers, but basically, right before you do that, it's words. That's data, right?
You can't measure colors without number.
What?
You can't measure colors in other way than number tools for a computer to calculate, right?
I want to believe we can change all information into numbers, but I know it's not true. Okay. Next question. Okay, I have a question. How many people now want to join the IEEE? That's what he wants to know. Usually when I talk to these chapters, the people in the room say, why should I join the IEEE? Right? Is that a question you can answer?
Jim, we are strong. We don't need.
They're strong?
Yeah.
Must work then?
Yeah. We're not strong. People know. And my opinion
What is your opinion?
is that every ellipse is a fish.
What is my job?
Nothing is occasional. Nothing.
What my job is, as a distinguished lecturer, is to answer any question you have about the IEEE or, you know, related matters. I don't know, how many of you are in the CIS student chapter or the chapter? I know you are. Are you the only one?
Yeah.
Well, who are these people? How did you get them here?
From earlier.
Huh?
From earlier. Yeah.
Okay, so why should we join the IEEE? What does it have to offer to us?
What? I have not.
Why should we join IEEE? And what does it
Yeah, I'm not going to lie to you. If I was your age, I wouldn't join it. There are some, or most of these students, or all of these students.
Not exactly.
So there are some advantages. I mean, student, for example, our society, there are many societies in IEEE, almost all of them give student travel grants, for example. But you have to be a member to apply for them. So, for example, it might be a summer school in Germany or something, a CIS summer school in Germany. You can apply for a grant to go to it and pay for part of it. So there's that kind of stuff. The summer schools are a nice benefit, I guess. And you can get travel grants to conferences and so forth and so on. How many of you in this room could get a travel grant? If you all applied, maybe 1, 2. I mean, it's like any other kind of money. You don't have it, I don't have it. We want it, right? The IEEE is it's a big society and it's got a lot of power. And yeah, some of the societies are good and some of them are horrible. And it's all politics, just like government. Right? I never liked that part of it, but I've been in it for a long time. Really long time. I know I didn't answer your question, but I never joined, when I was a student, I never joined any society. I'm not a joiner. Okay? If you are a joiner, it's a join to join. Yes. Any other questions? Oh, there's some chocolates for you.
For you.
Not for me. I don't eat that kind of stuff.
If you want.
It can be for you. Are we done?
Yep. Of course.
Of course. Come have a chocolate.
Please.
Have
Come and enjoy.
have a water and a chocolate.
Yeah. Water,
What
chocolate,
are you better? You
nuts.
have a band named Water and Chocolates. Or don't have a water and chocolate. Well, thanks for putting up with me. And hope to see you again. Yeah, I hope to see anybody again.
Ще кажа и на български това, което споменах. Ние не правим никаква реклама на IEEE, достатъчно силни сме. Значи, за тия мероприятия са излятили над $7000, за да постигне тук, да не взимаме такса от по 100 лева, нали? Така че, общо взето, просто това е най-голямата професионална организация в света и само това се заслужава да си види сайт.
Нещо като DigiWin на Google.
Малко по-сериозно, защото
А вие парсите само форум.
I'm not so familiar with working with field.
Въпросът е дали има парад и трябва да има
I'm not something I thought of, I don't know.
А някакви клауди или нещо?
Имаме и отделен главно контейнер.
Контейнер или Моля, имаш спираш лесно.
Колкото искаш, аз имам децата, казваш къде искаш, какво значи ще бъде за Computational, може да работя
Да, просто самият контейнер за ресурсите можеш да дадеш повече.
You can try it. These people will give you all the stuff.
Там най-вероятно, например, съвсем да ви
Depends on what you want. I mean, different things will get you hard.
По-добре да се споделиш рекламата, така че да може да
Гледа на букет. Контейнера е част от операционната система и там се
това, което съм направил за последните 2 години,
те просто систем коловете вместо минат през виртуалната машина,
директно ти да
пускаш виртуалната машина. Тоест имиджа вътре си операционна система. Ти всъщност нагоре не можеш, защото горната система има в система. А вие достигнете се.
Няма комерциална.
Да, блокира.
Сериозно се развива.
Колко е поръчвал за сервис, който чакаш примерно една фирма на как се започва с секции, после ти просто заявяваш, че искаш повече. Имаш контролен пазар. И всичко е
После което мога да 4 бази на лопа. Да, доста веднага да мога да си оплъваш.
И мога да добавяш колко искаш много да.
То мога да добавя Computational, мога да си делам различно тезда си някакъв вебсайт. Работя с една база само.
С Bezdek, с Hadoop занимава.
Те се занимавам много с Java. Тоест, съпорт за тия неща не мога да.
Това е доста сериозно.
Това е просто. Проблема е, че системни администратори, това е колко да просто Java. Стана така широко.
Още компании са доста сигурно.
Едната компания се занимава с SoftUni, втората компания се занимава с Anomaly, третата компания с SoftUni.
Той ще се е.
Не сме един екип, реално. Няма много изисквания. прекъснала до web application, имат собствена версия, обаче собствена версия на engine, собствена версия на Microsoft, собствена версия на QRX, нямаме сърч, който да не сме пачнали хейли за multi-ползване този за нас. Всичко ние си имаме делта на нови системи.
Интересно как се казва? Сайдграунда съм чул. Цял се страни в България.
Ние точно ще се дълго ами, проблема не е всеки път има липса, огромна липса на всички пълно ниво искам да ги направя. Да ми разне работа да мога и пак за по-интересно. Школата мога да е по-достатъчна за интересната част, безинтересните глупости, това да му бъде отговор на клиента. Трябва да правя не, аз искам да се работа.
Не, ти каза, че тук работиш на така нещо.
Може нямам много възможност. Тя защото този семестър е на съотношение.
Понеже в началото каза, че мисля, че се занимаваш повече с... Да се каза за част с проектът, и сега с тракването на различни хора.
Ами да, това е золко, това е една седмица сектор.
Да, той е съвсем.
От всеки за ладни система, силата на сигнала, която имаш от твоя телефон до АП. Едно тук, само че ако се преместиш там, се цели друго. Цялата обаче, когато имаш само едно АП, нещо, че това не е базирано на тази сила на сигнал, защото не това е окръжно стане.
Няма как да става.
И за това е обаче на Apple West Shield 12 евро. Аз мога да седа сигурно на сигнал на всяка нещо, което очаква за място. И без да калкулираме ситуации, когато някакъв сте много хора на едно място, радио 17 трябва да се шокираме.
Това е супер голяма част, понеже аз се занимавам с локализация на роботи и така нататък. И всъщност това е една от идеите.
Препятствията са проблематични. Това е неудобна среда за детектване на разстояние. Имаш радио, но не е желание.
Това е за многолучно
Проблема е, че в много висока частота е това 2.4 и този проект е да взимаш информация от протокола. Протокола внася допълнително влошаване на данните, които получаваш. Ако вземеш директно на радио, и всеки един от излъчвателите е нормален радиоизлъчвател, сега радиолокацията е много лесно да обаче в единственият хубав начин е в GSM, в SS7 стека, имаш Location Services вътре вграден от протокола. В 802.11 нямаш Location Services. И той самият протокол слага идеята да има такова нещо, тъй като ми дава ти се опитвам да екстраполирам за данните, което обаче скъпва данните.
Той само ти казва ниво на сигнала и
Шайната цела е да може да преценим, базирано на всички 20, които видим в лабда си, да може да направим графика как се местят в една зала в друга зала и колко се намират в една зала.
Това е част от Open Fest.
Да, това е просто да... Това е да кеф, защото на толкова много апета и проекта лесен да го направим. Не го правим да почнем. Иначе трябва да си мисля след това, като го направим, после да ползвам за офиса, защото ние имаме голям офис и имаме 20 изложби. Ако искам да говоря с менеджера на заплата, трябва да знам дали е текуща сграда или съседната сграда. Което би било много яко, да ще отворя една уебстечка, да трябва да е закачени мисля там. Двете сгради са една от друга, когато се тука, може да се съчетаваме, което е другата сграда, което е напълно окей. Обаче аз трябва да знам, че ти си тук в тази сграда.
И всъщност има вече някакъв собствени това, просто може да ви изпили тяхната, защото проблема, който имаше, особено ако залите са квадратни, кръгулни, тогава е доста по-лесно, колкото са геобразни и има нетрадиционни форми.
Това не е вярно. Няма зависимост от формата. Също и така, имаш това ти е едно, което искаш да блокираш. Това ти е едното АП, това ти е едното АП. Тук имаш още едно АП. Този клиент се вмести спрямо тези трите АП. Това са винаги с достатъчно силна. Така че аз винаги мога да преценя, защото чувам едно АП от това. Къде точно се намира този клиент?
Единствено,
да знам разстоянията между всеки един от тях. Това е един initial measurements, които са с един перфектния клиент, т.е. когато няма хора, може да направим пожар на сета, когато няма никой, да отида там, да отида тук и да засека този клиент, да оставим един телефон.
Да си намериш графика, нали?
Да си направя dimensions графа и след това просто трябва да сметна къде се намира това, като единствено направя пропорцията на сигнала спрямо разстоянието. Което не е мега сложното нещо.
Не. Да, всъщност, за това да намериш в коя стая, няма да проблем.
Най-сложното нещо в момента е да направим така, че АП-тата едновременно да може да ги ползваме за АП и да може да ги взимаме за measurement, защото иначе те взимат measurement само за всеки закачен към тях, ама този клиент може да не е закачен към другите